All right, welcome back to part 4 of 5 of Atoms. How do we know what we know? Previously, we have talked about 2 of our 3 learning intentions. How did the idea of atoms originate? We talked about Democritus and his idea of atomism. We learned a little bit about Aristotle from our readings. And then for learning intention 2, we talked about Dalton and Einstein and how they gave us further evidence that atoms exist. You also should have read about things such as Lavoisier, Mendeleev, about the periodic table of elements and the work that those people have done. Today what we're going to talk about here is how has the model of atoms evolved over time. We looked a little bit already at J.J. Thomson. He had his plum pudding model, which differed from Dalton's in that it had a subatomic particle called an electron that was spread throughout like a plum in plum pudding, spread throughout an atom. Today we're going to try to get to the bottom of this whole thing. What is an atom? And we're going to do that by looking at a series of scientists and how they built on each other's understandings and findings and use new technology to advance our understanding of the atom. Now, we're going to start with radioactive elements. Now, at this point in time, we're at 1903, which is roughly when Einstein came out with his Brownian motion paper, which was 1905. Thomson had just discovered the electron, and there's another thing happening with atoms and elements right now, which was radioactivity. And there was this guy named Henry Becquerel who accidentally discovered radioactivity. And what happened was he was in his lab one day, he had these uranium salts, and he set them on top of a photographic plate, which was covered in paper, completely sealed off from any light sources. And he tucked it away in his desk, not thinking much of it. And then later, for whatever reason, he developed it after it had never been exposed to any light. It was a photographic plate, so the only reason it would be dark was if it had seen some light. And it shouldn't have, because it was tucked away in his desk in a basically wrapped up tightly. No light ever saw it. However, these uranium salts were sitting on it, and what he found was this image right here. And what you see here is essentially the silhouette of the uranium salts that he had set on top of this photographic plate. And he was perplexed by it. He said, I know for a fact that there were no electromagnetic rays from the sun or from lights or whatever that hit this plate. The only thing that happened was I put these uranium salts on it, and they must be giving off some sort of invisible particle that I can't see that is causing the plate to light up. And he had discovered radioactivity. He didn't know what it was. He didn't even call it radioactivity at the time, but that's what he found. At a similar time, Madame Curie, Marie Curie had heard about this, got really interested in it, wanted to study it, and here she is on the left, right here, with her daughter Irene, and the family of Curies in total, I think, won a total of 5 Nobel Prizes around their work in radioactivity. So as a family, they were absolute giants when it came to radioactivity. And we're going to talk a little bit about Curie and her contribution to atomic theory. It was Becquerel who first discovered radioactivity, but in my mind, Curie did a little bit more with it, or a lot more with it. She investigated it in great detail, her and her husband Pierre, along with their daughter Irene. She came up with the term radioactivity, and she also discovered or gave the first evidence that atoms are not in fact indivisible, but they can be broken apart. This is the first time all the way back from Democritus where we said that he said that atoms are indivisible, they can't be broken apart. Dalton said this, even Rutherford believed this. I shouldn't say Rutherford, Thomson. And this was the first evidence that maybe atoms weren't indivisible. This was a pretty big finding. If you study Curie's life, it's really interesting. She was the pinnacle of grit and determination. She toiled away for years, isolating new radioactive elements that she had sort of postulated that existed out there, and she was determined to find them. She had done some calculations and knew that these elements must be out there, but no one had found them yet, so she said it was her life work, essentially, to find all the radioactive elements that she could. And she found two of them, radium and polonium, polonium being named for her home country of Poland. And she was recognized for her work, receiving two Nobel Prizes, one for her sort of discovery of radiation, along with Becquerel. They both received it, along with Pierre Curie, her husband. The three of them received it for discovering radioactivity. And then she also won one for discovering these other elements, radium and polonium. She was the first female to ever win a Nobel Prize, first person to have ever won two, and on top of that, they're also in two separate fields, physics and chemistry. That's a pretty incredible achievement for one person. So not only did she give us some evidence that made us struggle with our concept of atomic theory in the fact that atoms are not indivisible, they can be broken apart, but she also gave us a new technology with which we could probe elements and atoms and determine new things about them. And what she did was she gave some of her isolated elements that she had been working with to other scientists. And they could focus these beams of radiation that she had found, and that gave us a new piece of technology. So just like in other stories that we've talked about in astronomy, we get this new technology and it leads to new discoveries. And believe it or not, radiation is something that allowed us to discover even more interesting things about the atom. One of the people who got their hands on this was Ernest Rutherford, so we're going to take a look at him real quick. And Rutherford, I'm going to move this over because I got a great little pun. Okay, Rutherford strikes gold. In 1911, what he did was ran a little experiment. It included a gold foil, and he discovered a new subatomic particle. And what he found out was not only is there the subatomic particle of the electron, there are other things that we haven't seen before. And this is what he did. See where I can fit here. Okay. What he did is he took some radioactive elements. He actually received some of his radioactive compounds from Curie, and he put them in a lead box right here. In this red box, there was a hole drilled out, a narrow opening. And what this did was the radiation coming off of the elements, I think it was radium or uranium or something, were these alpha particles that all they had really known about them at the time was that they were these very small particles that looked a lot like a helium atom. So they are really small particles, and since it was just a small opening in this lead box, it essentially focused all of the radiation coming off of this element and turned it into a beam. And he thought, okay, we'll put something really thin in front of it, a thin piece of gold, and we'll see what happens. I'm not entirely sure what happens. What we would think would happen was that this beam of particles will probably just go straight through. It won't really interact with anything because they're so small. But what they found was very different. We look at our experimental setup again. We've got our lead box. We've got our alpha particle emitter right here shooting a beam of alpha particles, the purple line right here. And in between that, we have a thin gold foil that's very, very thin, you know, like an atom thin or so. And then we have this detection screen, which essentially serves as a film in which we can capture the response. What do these alpha particles do after striking the gold foil? And if you can read right down here, it says 99.99% of the alpha particles go right through the gold foil and strike right behind it. What they did, and thanks to their setup, is that they didn't just look right behind. If they would have done that, they would have been like, okay, maybe there's some deflection over here. I don't know, it's kind of interesting, but not super interesting. But what they did, and they're smart about this, is they wrapped it all the way around. And what that meant was that, in fact, there were some of these alpha particles that were bouncing almost straight back at the emitter, almost straight back, bouncing right off. And that was very surprising. In fact, Rutherford even said about it, it was as if one had fired a large naval shell at a piece of tissue paper and it bounced back. This thin gold foil was so thin that it was sort of incomprehensible that this particle traveling really, really fast, that was really, really small, would go and get bounced back. Didn't make sense. So what could be the explanation of this finding? At this point in time, Rutherford was actually a colleague of J.J. Thomson, who we had just learned about, and J.J. Thomson had the plum pudding model. Here's our plum pudding model from J.J. Thomson. And according to his model, these alpha particles will go right through any of these gold atoms. There isn't really anything to stop it. There's the pink part that has a slight positive charge. There's the electrons, which are tiny, tiny things. And we would think that the alpha particles would go right through it. But that's not what they saw. It turns out, actually, that some of the alpha particles bounced off. And since this didn't make sense with Thomson's model, Rutherford had to introduce a new model. And this is a key point in science. Whenever we get evidence that doesn't make sense with our current models, with our current understanding, we have to develop a new reason. Okay, so we see alpha particles are getting bounced back at us. Why might that be? And what happened was Rutherford proposed a new model, and it looked like this. He said that atoms must have a nucleus, which is a concentrated mass at its center. Here it's depicted by this red dot. And what he argued was that the 0.01% of alpha particles that got reflected back at them was actually running right into this nucleus, and the rest of them were going straight through the atom. This allowed Rutherford to make two conclusions. One, atoms have a nucleus, which was a new finding when we compare it to Thomson's model. And two, that the majority of an atom is actually just empty space. And I had mentioned previously in part 3 that if you were to remove sort of the electron cloud of any atom and just condense it down to its nucleus, and you did that for all the atoms in our body, your body, my body, and put all those atoms, just the nuclei of our atoms, we would be the size of a grain of rice. We'd be really tiny. In other words, the majority of our bodies, the majority of this desk that I my computer's on here, the majority of the house that I'm in right now is empty space, and only a small part of it is really massive nucleus. That was a whole new concept to scientists at the time. So here's maybe a more better looking model of the nucleus, and you can see that there are some new additions to this. So Rutherford found out a couple other things, and he won Nobel Prizes as well, and he also made some predictions. Rutherford was, as I mentioned earlier, he worked under Thomson, but he ended up getting his own lab, and it turned out that throughout his life he had 11 students who worked under him at one point or the other who went on to win Nobel Prizes. So when I said Rutherford was in the right place, he was asking the right questions at the right time, and he had this new tool that nobody else had, which was the alpha particle emitter, and it led to a lot of breakthroughs in our understanding of the atom. And some of the other things that he found were protons. So he knew, or he had found the nucleus with the gold foil experiment, but he also ended up finding the proton and said that the proton is one of these particles, subatomic particles, of which atoms are made. He also theorized, but did not specifically find the existence of a neutron, which is this red sphere right here. And in essence, he came up with what we kind of think of as our standard model of the atom. He laid the groundwork for it. We now know that protons and neutrons make up the nucleus of an atom, and then around that electrons orbit, but the most of an atom is filled up with empty space. The neutron, Like I said, he theorized. I think someone named Chadwick in like 1936 actually found it, but it was because of Rutherford that he was even looking for it. So he laid the groundwork for our current understanding of the atom. When he passed away in 1937, the New York Times actually wrote an obituary on him because he was such a famous scientist, and they wrote this: "It is given to but few men to achieve immortality, still less to achieve Olympian rank during their own lifetime. Lord Rutherford achieved both. In a generation that witnessed one of the greatest revolutions in the entire history of science, he was universally acknowledged as the leading explorer of the vast, infinitely complex universe within the atom, a universe that he was the first to penetrate." So that's a pretty awesome quote to have said about you, first of all. But also, I want to think back to what J.J. Thomson had said previously in his quote that I had, which was that he said, "Every new discovery in science leads to new questions, and we need to be willing to walk through the door of those questions and learn what else is out there." And Rutherford was a guy who not only did he find new doors in a sense, but he also walked through them and asked more questions. And that is what made him such a great scientist. Okay, so now we're going to take a pause. We're actually going to make this a 6-part series. We'll call this 0.5 part. We're going to talk about one more person, Niels Bohr, who put the final touches on our theory of the atom. And we're going to take a little brain break right now. So you can pause, you can get up, you can stretch, do whatever you need to do. Then you can come back and watch the rest of this video. And we're back. Okay, so hopefully you had a chance there to take a little break. We are going to continue our investigation on atoms. We learned just recently about Rutherford and his experiments. He determined that atoms have a nucleus and that they're composed of protons and neutrons. And we're going to take a look at Niels Bohr, who tells us more about the electron. What is it doing? What is its role in all of this? And so here's a picture of Niels Bohr. Turns out that he was kind of a goofy guy and very energetic. He liked to do, play sports and run and jog and do a lot of physical activity. And there's a story that when he was a professor once, him and a colleague were walking down the street and they were both mountain climbers, and they came across a bank. And one or the other challenged. They said, let's see who can get to the top of that bank the fastest. So they started climbing the side of the bank actually, and they're racing up the side of the bank. And the cops got called on them because somebody thought that there were bank robbers trying to break into the bank. And the cops showed up and they're like, "Oh, that's just Niels Bohr. That's just what he does." So it's just kind of funny to think, there's lots of different personalities in science. And Niels Bohr was certainly one of those personalities. Okay, now Bohr noticed a problem. According to Rutherford's model, in classical physics, Rutherford had said that electrons were orbiting around this nucleus. And he said, well, electron has a negative charge and it's moving, so it would be emitting energy as it circles the nucleus. And it would slowly lose energy, eventually collapsing into the nucleus. And that would mean that the atom is not a stable thing. It would fall apart or it would implode or something. But we know that atoms are actually very stable. And so it didn't make sense to him. He wasn't sure what was happening. And as we've seen before, when scientists come up with a model and they find a reason that it doesn't make sense, they have to develop a new model. And Niels Bohr did just that. And his model looked something like this. Bohr's model essentially said, or he took the ideas of another physicist named Max Planck, who was a very famous physicist in himself. Planck had developed some mathematical explanations of light, which said that light only came in discrete amounts. When we talked about light being both a wave and a particle, Planck had come up with these equations that said light could behave like a particle. It could only come in discrete amounts. In other words, it was quantized, or it was a quanta. Bohr applied some of Planck's ideas to create an atomic model which had discrete orbitals in which electrons could be found. So between Bohr and Planck, they laid the groundwork for quantum physics as we know it today. And what Bohr said is that an electron can be in any given orbit here, but only at that orbit. So we have 3 different orbits. An electron could be here, and it could bounce up to this one, but it can't be in between. Or it could be here, it could bounce up to the second orbit, but it couldn't be somewhere in between. It had to be at these discrete points. And that meant that in order to bounce up a level, it had to absorb a certain amount of energy. And this amount of energy, it turns out, could be equated to the amount of energy contained in a photon. So if a photon were to hit an electron at this lowest energy, and that photon had a certain amount of energy, let's say, it would make it bounce up to the second level. If this electron, for whatever reason, lost energy and it fell into this first orbital here, that means that it's going to lose energy and it's going to emit radiation in the form of a photon that's exactly equal to the amount of energy that it loses. Let's look at what that means. Nope, I got ahead of myself. Let's talk about what does it mean to be quantized first. Quantized means essentially that there's not a continuum, there's only specific amounts of something. We think of money. Money in our dollar bill is quantized in the form of a penny. It's the smallest thing you can get. Everything you could say is a factor of a penny. A dollar is 100 pennies. You can't have half a penny in your pocket, right? It has to be 1 penny or no pennies. So in that sense, money could be considered quantized. We also have this picture here of some stairs. Stairs are quantized because you can't be at half a stair. You're either at the first stair, the second stair, the third stair. There's no in between. The opposite of stairs might be something like a ramp. And a ramp is essentially a continuous gradient, whereas stairs, it has specific levels. We go back and look, we've got specific levels at which electrons can orbit. And that's why we say it's quantized. Pie, on the other hand, we could have a really big slice of pie, we could have a really small slice of pie. There's no way to determine how big a slice of pie might be. So we would say it's not quantized. You could have any continuum. You could have a slice of pie this big, or this big, or this big, or this big, so on. It's a continuous amount, so it's not quantized. That's what quantized means. All right. Now, what does this all have to do with atoms? What does it have to do with our story? Well, Bohr's model is what actually leads us all the way back to Cecilia Payne. Bohr's model could correctly predict the emission and absorption spectrum of various elements. In other words, if you have a helium atom and it's got some electrons floating around on it, if this helium electron gets bumped up to this second level, or this second orbital here, it would have to absorb a certain amount of energy. And that energy would be coming from a photon. In this case, the photon would have, we could say, like 2 quanta of energy. It would bump it up 2 levels, and then it would be removed from the spectrum afterwards. Or we could have an electron in the 5th energy level drop down to the 3rd or the 2nd, meaning that it loses 3 energy levels. It's going to release an energy or a photon at energy level 3, which would be the yellow. Okay? And what this meant is that astronomers could use his idea to determine which elements are present in stars, because you can look at the spectrum of them, which photons come in a higher emission and which ones get absorbed. And that's what Cecilia Payne was working on when she gave her thesis to the Harvard professors in 1925. She used quantum physics and she used Bohr's model to correctly determine the atomic composition of stars. She said that stars have 1,000,000 times more hydrogen than we had previously thought, and She got laughed at the time, but she continued her investigation. They got more evidence. Some other professors looked at it. Some other people got this idea in their head. They solved it in similar ways. And eventually the whole community came to understand that yes, Cecilia Payne was right. And if we use Bohr's model of the atom, we can explain exactly why. So she is quoted as saying, "There is no joy more intense than that of coming upon a fact that cannot be understood in terms of currently accepted ideas." And basically what she's saying is that as a scientist, there's nothing better. What we're all striving for is to find out something new. And that's basically the greatest happiness a scientist can have, is to discover something. And she in fact did discover something and did not get the credit that she deserved immediately. So she rightfully deserves a lot of credit for advancing our understanding of the stars. So overall in this unit, this little section here, we have talked about how we can look at very, very small things like atoms to understand very, very big things like stars. And atomic theory can help us actually understand our universe and vice versa. Scientists right now who are studying things at the atomic level also have to talk to scientists who are studying the cosmos at the universal level. And as a scientist, you have to be open to communicating ideas with people across disciplines all the time. And a big idea in science is being able to communicate and collaborate across different backgrounds. So if you're a scientist, you have to be willing to do this, and I just wanted to emphasize that point. Also, our model of the atom is not complete with Niels Bohr. There are things that have been found out since him, and we are currently understanding things about the atom. This is a picture of the CERN Institute, which is in Switzerland and Italy, and the director of that program. And here they're searching for things called like the Higgs boson, which are incredibly small particles of which atoms are composed. So we're still learning things about it. It's a very interesting field of research and very exciting. And I would say that you guys are going to know more about the atoms than I probably ever will. And you should be very excited about that. Okay, our reflection slide here. This is part 4 of 5. This is the last sort of educational set we have. And this is what we're going to talk about. Knowledge is open to revision in light of new evidence. Both Rutherford and Thomson worked together. They were colleagues and they were friends, but they had differing models of the atom. How do you think they got along? What about science allowed them to get along? Also, Payne's ideas flew in the face of previous findings in astronomy. How did the scientific community respond to her? So for paragraph 4, you're going to write about Rutherford and Bohr and how they built on Thomson's model. You're also going to say what evidence led to the need for the nuclear model. How did Bohr's model allow us to learn about the stars? Continued learning is going to be the OpenStax Chemistry book 2.2. And then there's also a simulation of Rutherford's experiment at the website link there. All right, so that's it for part 4. There's a lot of information in there. Maybe not all of it makes sense, but I encourage you to go do those related readings. You can ask me questions in class. And part 5 tomorrow is just going to be a wrap up. There's no new information. And that's it. Have a good day and get to work.